Welcome to the MPC 5607B training for the Freescale Cup. We're going to give you some hints on how to get started. I'm Steve Mihalik. I'm a field applications engineer at Freescale. I've been working with the Coriva architecture for about 17 years. What we're going to do today is go through an overview of the system, just general things you need to know about the architecture. Then we'll get into what about the pads and the I/O, cover clocks, something called run modes. Then we'll get into I/O for timed I/O, interrupts, how to do a task scheduler, and analog to digital converter, and then finish with DMA. We're not going to cover peripherals that are not needed for most people using the exercise for the Freescale Cup. Okay, let's go to the first section here, and it's just an overview of the device. We have a block diagram, and you can see here on the top we have some boxes, and then we have this crossbar switch and memory protection unit, and then we have some other boxes on the bottom. On the top, these are masters. The masters can initiate a bus access. So they will read memory, write to peripherals, etc. The bottom will be the slaves, typically the peripherals and memory. And using the crossbar, we can have parallel access. This is all transparent to you, but we can, for example, read an instruction from flash at the same time the DMA is writing to RAM. So this parallel execution or simultaneous access gives us, of course, more throughput. The crossbar itself, though, you don't have to worry about. It is transparent. The memory protection unit is an option. It is disabled on power up, but the purpose is for operating systems for preventing illegal access. For example, a program mistakenly tries to write to the flash, and it's not a flash program, so you can prevent that. Or you maybe try to DMA to some peripherals that you're not supposed to. So it can be used to protect regions of memory from illegal access. Then on the bottom here we have our flash. This is for the 5607B. The 7 indicates the memory size, in this case 1.5 megabytes. The bridge is just a simple connection to get through to the peripherals. Think of it like a simple analogy would be a hub for your laptop to go to a printer, keyboard, mouse, and so forth. Then we have our RAM here. Standby RAM is something we have a low power modes that you probably will not need for this competition. And in the low power modes, 8K is always powered. Looking at the peripherals on the bottom, the EMIOs, this is the timed I/O. And we'll get into this in a few hours. We have CAN for CAN communication. This works off of a message buffer architecture. So we have mailboxes. And you set up a CAN message and you say go, and the hardware will take care of it. And you say, you set up for receiving a message from an ID, and you say go, and hardware takes care of that too. LinFlex is for Lin 2.0 and also UART. You program the LinFlex module, and we have up to 10 of them here, for either to be a UART mode or a Lin mode. The DSPI is just your typical SPI where we're going to connect peripherals to each other on board. It's maybe you're hooking up to an SBC, a power supply, and you want to read some status information or current information. I2C is another simple protocol. And then we have 2 analog to digital converters. One is 12-bit, one is 10-bit. And we'll cover this later. Okay, so a few basics in this introduction. We are naturally big Indian. That means the most significant byte is on the left, and I'm numbering my bits from 0 to 31, or in some processors 0 to 63, but unlike all the other Freescale processors, bit 0 is the most significant bit. So you have to kind of reverse your thinking that, you know, in some processors, bit 0 is the least significant. It's most significant bit here. And we're going to, the assembly level, the compilers are going to write to general purpose registers, and of course they're all 32 bits, but once again, bit 0 is the most significant. So we are going to have a word, for an example, that will be loaded from address 0 of bytes ABCD. And if we load a half a word from address 6, we're going to load GH. So a word is 32 bits, 4 bytes. For startup, here's what happens. Our power on reset circuitry monitors internal voltage and then deasserts the external reset signal. And the default clock will start out to be 16 megahertz. This is an internal reference clock. Sometimes we call it the fast internal reference clock. A little sloppy, you can trim it. And then we have boot configuration pins. You shouldn't need these. This is in case, for example, your flash is erased, there's nothing in it, and you want to program it. And it allows you to strap the pin so you can do a serial boot. You download code into RAM and then you execute from RAM. If the boot configuration says, hey, it's a normal boot, then we'll have a 16 megahertz clock, and the hardware will now look for some configuration information, and it looks in one of 5 locations. Usually we'll just use location 0 and forget about it. But if it's not there, it will look at the other locations. And the way it identifies this is the boot information is that there is a 5A written in a particular byte in this first word. So all our startup files will do that for you. You don't have to worry about it. And all our startup files after this 5A will do the second piece of required information for the boot configuration is specify the start vector of code. So it's basically, it's a constant for underscore start. So the first 2 words here are going to be this, this boot configuration ID of a 5A somewhere in this first word, and the second word will be your address of your start vector. We have something called ECC, error correcting code, where it's transparent to you, and this means if 1 bit fails, we will fix it for you on the fly, because for every 32 bits in RAM and flash, we have extra bits, like I believe it's 6 extra bits, that will automatically, in the hardware, while that's being accessed, it will check it, and if 1 bit is wrong, it will fix it. And it's you never know. You can enable reporting if you want for 1 bit, but the program will keep on executing. If there are 2 errors, mathematically, you know, highly unlikely, then it will holler, and you'll get either a reset or an interrupt, or we can get something called a safe mode request we'll talk about later. So, however, when you use error correcting code, you must initialize all of SRAM before using it. And this again is in the startup code of the projects we're giving you, or if you download through the debugger, you must be able to have the debugger write to all of memory, or your code write to all of memory before you use it. And that will set the initial ECC bits. Flash has ECC as well. I'm not going to go over all the material. You can read it later. I'm going to, kind of like the Oracle and the Matrix, tell you what you need to know. and there's other information in this material that you can look at later. One question is, why did I get reset? There could be a number of reasons. And you could get the power on reset. In other words, the voltages are coming up. Maybe there's a watchdog that went off, or low voltage was detected. Those are called destructive resets. That means that we won't be able to recover. We guaranteed we cannot recover. Other resets you may be able to recover, and these are functional. And they both have associated registers to tell you, why did I get reset? We have included in the CD with the Trek boards a tool called Rapid. This has two parts. One is a pin wizard, and this is a free download from Freescale that will allocate pins to peripherals. It's a graphical interface you can see on the next slide here. Has all the pins here. It's hard to read perhaps on the screen, but we have I squared C. We can click. Do we want it to be on an input or an output, and which pin? And so as you go through all the different I/O modules, you can set them up. And if there's a conflict, it will holler and complain, so you can fix it and won't let you go forward. The result is a spreadsheet and documentation that you can then edit with your signal names. The other part is a rapid initialization. This includes a free 30-day trial. There's a GUI interface so you can set up your system clock, your interrupt handlers, and it will generate code to initialize and give you an interrupt handler. And this can then be used for documentation, because we have a documentation. It's quite extensive HTML option that will document what you're doing on the code.